Okay, so today what I'm going to talk about is a very important skill set in engineering analysis. It's called FEA and CFD, Finite Element Analysis and Computational Fluid Dynamics. So, pretty much this is to simulate solid materials like displacement or pressure, okay? Or like displacement or stress, I mean. And then CFD is to simulate like aerodynamics and fluid mechanics like this. You see, we're simulating the flow of fluid inside a valve. So that's the difference between CFD and FEA. So I encourage you to read through the side presentation for this lecture. It talks about these two in much more detail and all the cool simulations you can do, like buckling and cloth simulations and things like that. So I encourage you to read through that slide deck. But what I'm going to focus on in this tutorial is pretty much how to do a simulation from start to finish. Alright, I'm going to show you how to simulate, a CFD, an FEA, and a CFD. I'm going to show you how to do both. The basics, the absolute basics, but enough to get you going. Okay, so by just knowing these basics, you can really do a lot for a lot of your designs. For some of the basic fixtures or machine assembly and test machine systems, you can really optimize your design, because it's not just about creating fancy simulations, it's about using this. You look at your meter here and you can see where you can optimize your design. You can see that there's barely any stresses going on here, so you may want to reduce the material, kind of like you do with an I-beam, right? So you can optimize. Or here you can see there's a lot of stresses here, so maybe you want to add more material, okay? You may want to add another rib, or you may decide that from the displacement there's too much deflection and it's going to cause a leak path, or it's going to cause something to lose its center of gravity. All right, so this is why we're going to learn how to use this tool, is so we can optimize. So before I talk about how to build simulations in SolidWorks, I wanted to just talk about why this is important and the types of simulations you can do. So first of all, this is a specialty of mechanical engineering, and they call them the CAE analyst. A lot of times you see a job description for CAE analyst, this is what they're doing. So it's a specialty. A lot of times it requires a master's degree, but at the same time, you'll make a little bit more money. So specialized engineering make a little bit more money than generic engineering that is done through manufacturing. So a lot of companies like NASA or corporations, they have an R&D department that has a lot of these CAE analysts. So CAE is just one of the 3 engineering programs that are out there. In engineering, there are 3 kinds of programs: CAD, CAE, and CAM. These are called Digital Product Design Software Packages. So CAD is what we've been learning since the beginning. It's a program, it's computer-aided design, and it's used to create models, drawings, and assemblies. Whereas CAE is mainly used for simulation work. It's used to simulate your models. It's not used for modeling. And then finally there's CAM, computer-aided manufacturing. And this is used for generating G-code, so your CNC milling machine can take your model and turn it into a real product. So again, like I said, CFD is to simulate fluids, and Star CCM is the Ferrari version of this. Okay, there's also flow simulation. And then you also have FEA, which is to simulate solids. SolidWorks simulation is the generic tool, and then Abacus is the Ferrari version of this. And the reason it's the Ferrari version is because you can do plastic deformation, like I'm going to talk about later. Again, but really what I mean by plastic deformation is you can get permanent deformation like what you see here, instead of elastic deformation, which springs back to its original state. So when you do an FEA, you need to set some parameters. You need to set the material, the restraints, the forces, and the mesh resolution. When you set a CFD simulation, you need to set the boundary box, the fluid cavity, the inlet, outlet, fluid pressure, and the fluid type. Okay, so those are pretty generic specifications that you spec on pretty much any kind of simulation, really. So another thing you gotta realize is with these Ferrari programs, you can refine a mesh. You see how you can refine this mesh? So this gives you a lot more granularity and a lot more information about your simulation. You cannot do that with like standard generic FEA programs. So one thing you gotta realize is there's the real test and then there's the simulation. There's pros and cons to each. Like a real test will give you noise, okay, and it'll give you variables that a simulation is not going to give you. So it's always good to do both tests to get as much information, as much data as you can, because this way when you have like multiple sources of truth, you tend to make better decisions as a design engineer. So just be aware of that. But at the same time, sometimes real tests are too expensive. I mean, you can't just crash a jet just to test a few things. Sometimes that's just too expensive. So sometimes you're limited by your resources, and you got to work with what you have. But you can't really go wrong with digital simulation. I mean, this is just a really, really effective way to get an idea of how well your machine's going to perform. So you can simulate buckling, you can simulate wind, inflation and pressure, you can simulate, spring characteristics of a racket, you can simulate the tensile strength of a belt. Here's a little FEA where you can kind of improve the aerodynamics of your vehicle, or on landing gear. So again, it's really hard to visualize this fluid, isn't it? I mean, how do you even know how that fluid, works? So again, like I said, a real test is good for simulating noise, but it's not good for simulating scenarios that are very difficult to simulate. Like, for instance, what if you want to test this landing gear on Venus, that has these weird, gases, weird pressures and temperatures? I mean, how are you going to set that up? I mean, that's going to be kind of hard to really set up. So in the computing world, you can set up some really bizarre scenarios that are just way too difficult to do in the real world. So looking at this, we're given some sort of lift. All right, so let's study this lift. If we open the start file, it's called start SLD ASM. That's an assembly. All right. That's the thing. When you start these simulations, you have to know where the object is restrained and where the forces are applied. There's not going to be a nice schematic where it shows you, all right, there's the forces, there's the restraints. It's not like that. So that's the first step. You got to understand the design. Understand where the forces are applied and where they're not. So this is just a lift. You got 4 pegs. It lifts some cargo. So you know that the forces are going to be applied here, and then you know that it's going to be restrained in these locations. So there's a slider restriction here, and then it's anchored on these 6 bolts. So we're going to simulate this cantilever beam. And we're going to test our deflection and our stresses and see how it compares with the rib and without the rib. So I created a configuration for that, you see. Ribless and rib. Alright, and we're going to run 2 simulations. We're going to compare the numbers, and we're going to see how important adding a rib like this can affect the performance of the product. So to begin, we have to turn on our simulation tools. This is a tools add-ins button. See this simulation? You gotta turn that on. And let's see what we get when we click OK. Oh, did you see that tab pop up? This is how we're gonna do our simulation. Okay, and really all you gotta do is just follow these steps. They did a nice job keeping this in order, alright? So it says, alright, create a new study. This is a static study. And again, if you read through the side presentation slide deck, you will know about these other tests you can do, like the fatigue, thermal tests, and things like that. So we're going to click OK. And did you see what happened? It created a new tab. It's no longer on the model. So this is its own thing. And also you'll notice these buttons are enabled now. They're no longer disabled. So we're going to pick material. And again, it's important to pick the right material, because every material has different like tensile strengths and yield strength, and you know, they just behave differently. And the reason this is important is because when you simulate, you have to understand the material, because different materials are going to deflect in a different fashion. So we're going to hit apply. Okay. And now that we've applied the material, we're going to move on to the next step, which is to apply the fixtures. So per the assembly, we notice that there's a fix. See, it even gives you diagrams. It says, hey, this is anchored. This is held down in the 6 degrees of freedom. So I'm just going to put a anchor on these 6 surfaces. It's going to fix geometry, as opposed to the roller. There's a roller here. As you can see in this diagram, it says, hey, it's just rolling. It's not restrained on all directions. It's sliding on a surface. So there's a roller there. Next, we got to apply the load. So in this case, it's going to be a force. And we're going to apply 10,000 pounds of force on each peg. 1. Whoops. 2. 3. And 4. 10,000 pounds. It's not going to be per item. It's going to be total. It's going to be distributed. So that's what you got to do. It's a material, it's restrictions, and it's the loads. And you can create a mesh if you want. You can refine the mesh any way you want. You can make it a fine mesh or a coarse mesh. And what you'll get is what you see here. So you'll get slightly more accurate numbers, but at the same time it's going to take longer to calculate. So I just like to stick to the default. And if you just hit run this study, it's actually going to just default the mesh. Okay, so that should be good enough for what we're trying to do. So as you can see, it didn't really take a long time, but it's a very powerful skill set. And obviously you can really modify this and refine it, you know, and add granularity on each of these nodes to really do a serious simulation. But for most of the time, this is really more than enough. So let's see what we get if we animate this. If you want to save an animation, you can right click, hit animate. Alright, this gets a little weird. You gotta hit stop, you gotta hit save file, then you gotta browse. I'm gonna hit to the desktop, files, dump, animation. Yeah, I'll just call it FEA for now. Gonna hit save. And try to reduce these numbers just so the memory size is not so bad. But anyways, you browse for file, then you hit play, and you see how it's creating frames. That's how you know it's creating the file successfully. So actually, if you look at the process, I'm showing you the process. Oh, I'm sorry. Over here, see, step 1, step 2, step 3, step 4. So it's a little bit picky like that. You do have to follow that step, but you know it's saving after you see that yellow box. Okay, so now let's do some analysis. Let's say we want to know, let's see here, we want to know the maximum stress location. So you see I click this checkbox and it tells me this is where the highest stress concentration is. So after so many cycles, this is the first place it's going to fail. And then here it's showing me the minimum. This is the least likely place to fail. Okay, so again, you use that to optimize. You say, all right, I'm going to put an I-beam here. I don't even need material here. It's a waste of metal. Whereas here you may want to beef up that rib or maybe add another one to the side. Okay, so that's what you do. You know, when you're optimizing, you design, you iterate, you optimize, and you do that over and over again. Okay. So that's what this rainbow meter means. It's the red is the largest number, and then the blue is the lowest number, and then you try to find it on the diagram. So it's the same with displacement. Obviously, it makes more sense that the displacement is going to be highest towards the end of the beam. Now this is just an exaggerated video. Don't think it's going to deflect that much. I mean, it's only going to deflect 0.03, which is like almost like half of a 16. So if you put 10,000 pounds, it's going to deflect about 1/32. Okay, so that's very, very small. All right, so this is just exaggerated to make it easy to read. So let's kind of collect these numbers. Also, I was once asked about colorblind colors. So if you're colorblind, you can change it here on the chart options. Optimize for color blindness, and these colors are supposed to be easier to see for a colorblind person. So you can change that on the settings over here. But let's let's record these numbers, all right, so we can optimize our design. So let's see, the stress is 1817 psi, so this is with rib, and then the displacement is 0.031 inches. Okay, so that's what we get. Now let's run the simulation again without the rib. All right, so again, I'm gonna do the same thing. All right, static. I'm just gonna do the exact same simulation, and we're gonna look at the numbers. All right, so I just finished running the simulation without the rib. Okay, and we're gonna see what we got. So ribless. It's 3245 psi. Okay, so hot spot is still kind of over here. And then let's take a look at the displacement. As you can see, it's much more uniform now without the rib. We're looking at 0.090 inches. So that's almost 3 times more displacement and about 2 times more stress. So as you can see, the rib really helped improve the performance of this cantilever. So again, that's what you do. That's how you use this. And you constantly iterate. Alright, for the homework, you gotta submit. Well, first of all, in the homework, you gotta type in these numbers. Okay, it's gonna ask you what is. See, let's take a look. So, homework 8. Alright, so the things you gotta submit is what is the maximum stress value? And then it's asking what is the maximum displacement value? Alright, so you're gonna look at this meter and you're gonna type in this and you're gonna type in that, okay? Then you're gonna type in what is the zone? Where is the hot spot? Where is the highest stress value? And you're going to type in 1, 2, 3, 4, 5 for the zone. After that, you're going to upload the report and the animation. Okay, so the animation I already talked about. It's that. Okay, when you animate, whoop, I didn't mean to do that. It's it's this animation that you save. The report is this button. It generates a report that shows me your restrictions, your restraints, your forces, and you can turn these on and off per the instructions here. It tells you what to turn on and off. Okay, and then when you hit publish, and you can do designer too, alright? You can do all those things. And then when you hit publish, it generates the report. It takes snapshots of each attribute, alright? And the final result is this report here, you see? And this is what you upload. You upload that over there. Okay. So some students, they create an animation that's too large. Again, if that happens, just compress it down, reduce the frame rate. Alright, there's a lot of things you can do to reduce the file size. But once you have those three things, you can hit submit and you'll be done. So that concludes the FEA portion of this tutorial. Now what I'm going to do is talk about the CFD. Alright, so when you create any CFD, you need like a boundary condition. And in this case, we're using lids. All I did is I just modeled some cylinders in SolidWorks using the extrusion tool. But I made sure that I'm not merging. That's why they're separate bodies. It's still a part file, but I'm not merging. There's an option for not merging, and that's why you see these as separate solids. So they take the size of the orifice in this valve body. If this was an aerodynamic simulation, I would create a boundary box outside the object, like a outside box. Like maybe sometimes some students, they like to do heat dissipation. They want to see how does the heat dissipate from a heat sink to the fan and to the surrounding computer parts. So in that case, I would create a box for the boundary condition. But once you have the lids, you can then add them, and then you can do a section view so you can see what's inside. And then you can fire up the Flowworks, it's Flow Express, but there's a full-blown add-ins version which is called SolidWorks Flow Simulation. It used to be called Flowworks, but now it's called Flow Simulation, and that's got more buttons than the one I'm using now, but it's pretty straightforward. I mean, you just click these buttons and it tells you, all right, what's the cavity look like, and it tells you what are you trying to run through this valve. And in this case, we just have water and air, but on the full-blown flow simulator, you have much more gases, many more gases. So then you gotta pick the inlet, alright, and the inlet volume flow rate, and then you gotta pick the outlet, and you just hit run, just like the FEA. So okay, so just let it run through. So this does require quite a bit of computation. So it can take a little bit of time. But I think I already mentioned that Star CCM Plus, that one is kind of like the Ferrari version of fluid simulations for CFD. Whereas for FEA, Abacus is a little bit better because Abacus lets you do plastic deformation, meaning you can see permanent destruction of the material, which is kind of hard to do with SolidWorks simulation. So Abacus is a little bit more dedicated towards FEA and Star CCM is more dedicated towards CFD. But the toned down versions in SolidWorks are still not bad. I mean, you can definitely do a lot of simulation with this. Alright, so the simulation is done, and as you can see, you can really get an idea of the flow. Same idea. You get the rainbow meter here, and the red shows you the higher speed material. The blue is the slower material, okay? And you get some sort of eddy current here, some sort of turbulence. Whereas here you have more of a laminar flow. And laminar flow is always better because it's less friction, it's more efficient, it gets your flow going. But if your application is like designing a parts washer, maybe turbulent flow is better for you. So kind of depends on what you're trying to do. And you can also change this to pipes if you like, so you can really get an idea of the history of the path. Okay. So this is good to really understand where the flow is going, how is it touching its surrounding surfaces, and it's just a good thing to use. So whenever you're designing, it's always good to have multiple sources of truth, and it's always good to do hand calculations, run a simulation. All right, so this way when you make decisions, you have multiple sources of truth to back up your decisions, and that's only going to make you a better engineer in the end.